Okay, whether my slides are visible. Good afternoon, students. Whether my slides are visible to you? I'm audible. Slides are visible. Hello.
Yes, sir.
Okay. So last class we discussed about basics of memory hierarchy. What is basically hierarchy? All those things. So in that, how we are going to fix the hierarchy based on the size, and then we are going to discuss about that speed and then cost. All those things going to fix that for hierarchy. In that, what way the catch will be useful, and then if the data is not available in the catch, where it will be there, where we have to get from memory, and that and then we are going to discuss about that memory server, as well as if it is a personal mobile devices, we have to use that flash as a end device, end storage device. All those things we have discussed, and then we will have a graph. So what will be the processor, how that processor going to get the data from the memory, what will be the time taken, all those things. So for that we are have one graph also we have discussed, and then we have discussed about what will be what is that what are the three C's, like for example compulsory, and then capacity, as well as conflict, and then the fourth C will be the coherency I have discussed. So what is how we are going to improve that performance. For that we have discussed about what will be the larger block size. So before that we have discussed about what is block, what is for example access time, okay, what is set associative, and then what is NVS associative, what will be the set associative. So what is the difference between block versus word or something like that. All those things we have discussed. So followed by we have discussed about the three C's as well as the fourth C. How we are going to improve that conflict, sorry, the miss penalty. What is basically miss rate? What is miss penalty? All those things we have discussed. Okay. So I think there is no doubt at all. If it is there any doubt, you can ask me, or otherwise we will have some refresh class at that time. We will discuss. So go through that video. I want to tell you one thing again, whatever the class it is thing completed means you just check with that GCR in that class. So unit 4 means that unit 4 material will be available. I will post. Okay. Previously I have posted a given link, but it is not visible, somebody told me. So in that case, immediately I have uploaded the video in that GCR unit 4 in that madam link. Now today also I will, once that class gets over, this memory technology optimization, once I got the video, I will immediately upload. Okay, so you just go through. So tomorrow, one more announcement. Tomorrow we have the test, and then most probably 95% there will be exam during your class hours. If there is any changes, we will inform you. Okay, so everything will be immediately posted in your GCR. Don't worry at all. Okay, so you just prepare, so you can easily able to answer. So don't worry about the pattern and all. Just it will be combination of MCQs plus descriptive. So we will give you enough time for you to answer. Okay, so don't get afraid of the exam. Okay, you will just prepare and then you can get ready. Now coming to that unit 4, memory technology and optimization. So last class we discussed about what will be the requirement for memory, and then what way the memory will be helpful for in order to get the data, all those things. Now we are going to discuss about some memory technology. So in that case, we are going to discuss about first what will be the basics of memory. So we all know there will be something called as main memory. So main memory, if you check with that main memory, then hierarchy list, it is going to be the last. So you can ask, so why it is going to be last? So is that the size is going to be larger, and then in order to get the data as fast as, and then that is a goal. So that's why we are going to have some hierarchy. In that case, that main memory is going to be at last in the downstream. Okay, so next to cache, so we'll have different levels of cache. Followed by cache, we'll have something called as main memory. So that will be we have that, but that processor, it will get the data from the main memory and then it will execute. So that that particular point you all know. Apart from that, we have discussed something about virtual memory. So what will be that what will be translation, for example, how that physical memory address is going to be translated into, virtual memory address is going to be translated into physical memory, and that part we are going to see soon. But if you are going to have a virtual memory address, that you are compulsory, you have to convert it to a physical memory address. Okay, that is very important. So the processor, it will work along with the physical memory alone. That particular point you all know. And then if I am going to have a block, that block will come along with the tag. The tag will be given specified address. So after that, I will map. After that, that will be kept inside anywhere within the set. Okay, so a set will consist of a number of blocks, or otherwise we have some one single block that is going to be called as direct associative. And then if you have n block, then it is going to be called as n-way associative. All those things we have discussed. Okay, so coming to that main memory, down in that memory hierarchy next to the cache memory. So it will satisfy the demands of the cache. So for example, if the data is not available in the cache, so immediately the processor, it will check with that main memory. So if there is a cache miss occurs, that miss penalty will be there. So in that case, we are going to get the data from the main memory. So that is why it says, we are going to say is satisfying the demands of the cache memory. So apart from that, the memory will provide services to the input-output devices also. So why? Because whenever that input, I will get that the input, and then I will store it in the memory. So we are going to use several input devices, similarly output devices. So to and fro. So we are going to get the data, immediately it will be stored. After get processed, I will send the data to the output device from the memory. In that, one more important thing we have to keep it in mind. We are going to use the buffer. So buffer is very important. So it will, the latency will be reduced with the help of buffer only. Once the data is going to be sent, or otherwise once the data we are going to receive, immediately it will be stored in that buffer. From that buffer only, we are going to get data to the particular, or otherwise we are going to perform read or write operation. Okay, so that is some simple introduction. So in that case, whenever we are talking about memory, we have to think about one more two important attributes, or otherwise two important metrics. One is going to be called as latency. So what is basically latency? So latency is nothing but whenever we are concerned about the cache, so it is going to affect that miss penalty. So what exactly means? So we are going to get that data. If it is not available in that memory, so we have to check for in the memory, and then we have to get back the data. So how much time it took for in order to get the data, that is going to be called as latency. So that the entire process for in order to fetch, decode, and then I'm going to execute all those things. So in that case, what will be the time taken for another fetch as well as decode is going to be called as latency. And then that is miss penalty. You all know miss penalty is nothing but we are going to have the translation time. So the translation time from virtual memory to or otherwise taken from the main memory, that is going to be called as miss penalty. The next one is bandwidth, concern about the multiprocessor and input output. So bandwidth is nothing but what will be the size of the memory. So if you refer to the cache, level 1 cache, it will be in terms of KB, and the next level is going to be in terms of MB, 1 MB or something like that. And then further we are going to have increased size in terms of MB. Finally, we are going to have that in terms of TB or something like that, terabits. And then the time will be there. So how much time, how faster I'm going to access it. It will be in terms of nanoseconds to its seconds. That and all we have discussed, that graph and all it is given for you in that last class slides. And then if the size is going to be this much, how much time it will take, all those things we have discussed. That is going to be concern about bandwidth. So in a core concern of a multiprocessor environment, nowadays we are going to think about i5, i7 processor. We are going to have multiple cores with the memory with the maximum size. So whenever we are talking about latency, it is going to be estimated with two measures. So already I told you how much time. In that case, that it is going to be two measures. One is going to be called as access time. So what is basically access time is the time between the read. So I will read request, I will send the request, and then I will fetch the data. So I will fetch the data at what time it is arrived. That is going to be called as access time. So if the data is going to be stored in a memory, I will fetch that address. After that, I retrieve the data, and then I will what time I am going to get. That is going to be called as access time. So cycle time, that is going by minimum time between request to memory. What exactly that cycle time is? For example, if I am going to fetch the data, I will get the data from the cache immediately. Then it is going to be, for example, 1 nanosecond or something like that. If I am going to fetch the data, if it is not available, I have to go to the main memory and then I have to get and then I have to translation all those things. So these are all the time. So all these things are all factors to be considered. So if it is not available immediately in the cache, I have to get from the main memory. So or otherwise some other cache has to be some other memory has to some other local cache or something like that. It has to produce the data. So for that it will take time. No, so that is going to be called the cycle time. So immediately if I am going to get, then it is going to be called as access time. If I am going to due to some issues. So if it is not available, so not issue, it is not available if the size is not affordable or something like that. So in that case, I have to get from some other source. So in that case, what will be the time taken for in order to get the data? That is going to be called as cycle time. Okay. So any doubt you have? You have any doubt you have? What will be the what will be access time? What will be cycle time? Any doubts you have? You can tell me now. If we can continue then to the next slide. Do you have any doubt? Anyone unmute and tell me? இப்போ யாருக்காச்சும் டவுட் இருக்கா? ஆக்சஸ் டைமுக்கும் சைக்கிள் டைமுக்கும் என்ன டிஃபரன்ஸ்ங்கிறது புரியுதா? Hello. Okay, so we will move on to the next one. So already I told you we are going to see something about the memory technology. So these are all the basics you have to cover. We have to know something about the memory. Next one is technology. Whenever we are going to talking about technology, we are going to have two things. One is going to be called as SRAM as well as DRAM. Most of the time we are going to use these two RAMs, two type of RAM we are going to use. These two technology we are going to use for in order to store the data. So in that case, S stands for statics. That is very important. Now RAM, you all know, random access memory. Sometimes it will be called as read and write memory or something like that. So random access memory, you can get the data anywhere else. That is why it is called random access memory. So whenever we are talking about the SRAM, that S stands for static. And then how I am going to store the data, there will be something called a switch. So that switch is going to be on or off. So how I will get switch? Don't think I am going to have switch something like that. What we are using in our phone. So we have something called as transistor. So we are going to give that value to the transistor. If that exceeds that the value is going to be exceeds that voltage threshold level, it will be on and off. So that is going to be called a switch. So based on that, the bits can be stored. So if the transistor is on, I will store the data 1. If it is off, it is going to be stored 0. So in that case, there is no charge to leak. So here we are not going to use capacitors. We are using transistor. So in that case, there is no point of leakage of charge. So and then normally you all know, if I am going to use a capacitor, so we have to need some refresh circuit. So the charge. So we need some refresh circuit is required. So but it is not. We are not going to use here. That this is the two advantages. So we are not going to use. There is no leakage of current, and then no need to have refresh. All those things are going to be an important advantage of SRAM. And then it requires minimal power to retain a bit. So why? Because so that we have only small threshold voltage is required for in order to switch on. So in that case, we will require minimal power to retain a bit for a period of time. So in that case, this access time is very close to cycle time. Why? Because immediately I am going to get the data. So even that cycle time, if I am going to have, immediately I am going to get. So this is very close. But only important thing is, for example, here is one important thing we have to keep here. It requires 6 transistors. If I want to store a bit in SRAM, that requires 6 transistors. That is one important challenge we are going to face. So the cost is going to be a little bit more expensive. So it requires 6 transistors, and then but it will be faster. Whenever we are going to think about the cost, But if I'm going to think about that speed, it will be high speed. So we have to, there will be a trade-off between cost, always there will be a trade-off between cost versus speed. So in that case, so performance in that ways, it will be fast, but that little bit cost is going to be high. So previously, if you think about that SRAM, it will be used at all levels of cache. So if you are going to use, for example, in older days, so that SRAM will be used for main memory, as well as we are going to use it for caches also, the things. So there will be off chip as well as on chip is going to be there. So you all know what is basically on chip as well as off chip. But nowadays, if later part, all the levels of cache are integrated onto a processor on chip. So in that case, that speed is also a little bit high, and the largest on chip third level. So that if we refer all the three caches is going to be on chip, so that the size is the third level is going to be maximum 12 MB we will get. So the size is also going to be little larger size we will get. So in that case, we can avoid miss penalty. So the access time for L3 cache is 2 to 4 times than that of L2 cache. Why? Because the size is going to be more. So in that case, the time is going to be 2 to 4 times than that of L2 cache. So 3 to 5 times faster than accessing DRAM memory compared to dynamic RAM. Soon we are going to see dynamic RAM. So compared to dynamic RAM, this SRAM will be 3 to 5 times faster. So why? Because there we need some additional circuitry, all those things. We are going to see what are the challenges we are going to have in DRAM, all those things. So coming to that SRAM, so it is static RAM, and then it is going to have transistor is used to store one bit on and off, and then it will have 6 transistor, and then that access time is very closest to cycle time. That all these things are all very important challenges. One important drawback is here we are going to use 6 transistor. So in that case, the cost is going to be high. Okay, any doubts? Next we move on to SRAM structure. So this is going to be a structure. So if you, and this is not that much structure, but here I want to show you something. So here already I told you there will be 6 transistor, T1, T2, T3, T4, T5, T6, all those things. So we have something called as bit line and then B bar, something like that. So for example, this T3 and then T4 is connected to DC voltage, and then T1 and T2 is connected to common ground, and then the T5 and then T6 is connected to an address line. So whenever we are going to value some address lines, that the data is going to be read. So for that, you all know, so we are going to use the transistor switch is on and off. According to that, we are going to get. Okay, so this transistor are back-to-back inverter. So we'll call it as back-to-back inverter that is going to be stored the data. So state, logic state. So whenever that C1, so we have C1. So in that case, that C1 is high and then C2 is low, that will get that state 1. So if I want to get that value store 1 in this one, I have to make this bit line, and then that value should be high, and then that here it is going to be 0, that inverter line. So in that case, I will get the value 1. So if it is going to be get 0, so in that case, I will get 0 and then 1, and then automatically inverter. So C2 is going to be high, and then C1 is going to be low. So similarly, I have address line transistor also. We have T5 and T6 will have the address lines. So we have that address line will be give that value 0 or 1. According to that, I will fetch that particular value, and then I will write apply to value to B, and then I will value on B. So if I want to write, I will. This is going to be called, normally we will use that word called bit line. So bit line will get that value. According to that, I will perform read or write operation is going to be done. So this is the basic structure. So basic structure of SRAM. Okay. Now coming to the DRAM technology. So previously, I told you there will be 2 things. One is going to be called it as SRAM as well as DRAM technology. So if you have any doubts in SRAM, you just ask me. Hello. Before going to proceed with DRAM, if you have any doubts in SRAM, you just tell me whether I can proceed with the DRAM. Hello. So you have any doubts in access time, or you have any doubts in cycle time, or otherwise any doubts in SRAM, you can ask me now. 1 minute I will give you. Hello. Otherwise I can proceed with the next. If you have any doubts, You tell me, otherwise we will move on to the next technology, which will be going to be called it as DRAM. Hello? Shall we proceed? Say yes or no, ma? So, anyone?
Yes, sir.
We can proceed to the next one. Okay. Thank you. Now, coming to the next technology, we are going to call it as DRAM technology. So, what is basically DRAM? Here also we are going to store the data. But what is the difference is, so previously I will use transistor. Based on that on-off condition, I will store the data in terms of zeros and ones. So you all know, you have to know why zeros and ones are only used. Internally, the processor will process the data in terms of binary only. So that is why we are going to use that value 0 or 1. So in that case, this integrated circuit, we are going to use that bit store as a charge in capacitor. If the charge is full in the transistor or that capacitance, then that value is going to be 1. If it is drained, it is not there. In that case, the value is going to be 0. So use only one single transistor to store a bit. So according to the value of the transistor, that here if I'm going to apply 1, that immediately it will charge it. If there is 0, there is no charge at all. I'm going to get value 0. So we are going to pack more bits per chip. So why? Because for example, if I am going to use DRAM, I'm going to have only one transistor is used. So in that case, the packaging will be more. So I can use more. What happened already? The data what we are going to have, we are going to use more number of the memory bandwidth is going to be more. How? We are going to use one single transistor. Whereas in case of previous case, if I want to store one single bit, I have to use 6 transistors. So in that case, the bandwidth is going to be small. Whereas in case of DRAM, the bandwidth is going to be more, and then that will be the more advantage. So, but one important issue is, if I want to read that bit, after reading that bit, it will destroy that information. Once I have read the data, that there is no data is available. Again, I have to rewrite that data. So that is why we are must be restored. Again, I have to restore that information. That is very important. That is one important challenge here. So we have some banks, hidden banks will be used. We are going to see that will perform that kind of operation to again restore the data. So once the data is read, that it will inform. What we can means we will read. So we will read that information. Automatically the data will be destroyed, and then it has to be must be restored again. So that cycle time is longer than the access time. That is very important. So we are going to have cycle time longer than access time. Why? If I want to read again one more time, so in that case same data. So in that case I have to restore all those things again. Then only I can able to retrieve that information. Automatically the cycle time gets longer than the access time. So whereas in case of SRAM, that cycle time is very closer to the access time. Whereas in case of DRAM, but that it will be, there will be some difference. So that is why we are going to use multiple banks. So allow the rewrite portion of the cycle to be hidden. So we are going to have that immediately once that the data is retrieved, again the data will be stored. So we have temporarily I will store, the backup will be there, automatically it will be stored. So in that case, it will if it is not available, again I have to retrieve that information from some other source. That is why that cycle time is going to be longer than access time. So after that, one more important thing is we are going to have use the capacitor. Automatically leakage is going to be more. The charge leakage is going to be there. So for that, what we are going to do, we maintain the data. So I want to have some refresh circuit that periodically every 8 milliseconds that the capacitor has to be refreshed. Otherwise, the charge gets leaked. So in that case, I cannot be able to get the data. So that is one important challenge. Okay, so all the bits in rows can be refreshed simultaneously. I will use the rows and columns matrix that is going to be there. So in that case, I will get the rows. I will have the rows now. So that is going to be refreshed simultaneously. So we'll have that the data is going to be in that horizontal way. In that case, we have to refresh that circuit. Okay, so what will we are now? We are going to have a comparison. Okay, so before going to compare, I will tell you what are the features. So here the bits are stored as a charge. There I'm going to use transistor, where here we are going to use charge. So we are going to use only one single transistor. There we are going to use six transistor. So more bits are can be stored, all those things. Okay, I will compare again soon. Before that, we are going to see that comparison. We are going to see the DRAM organization. So DRAM grows in capacity. Dynamic RAM grow in capacity. Why? The transistor is going to be, and the number of transistors is going to be. If I want to increase, I can increase. So in that case, it is going to, according to the requirement, I can increase the size. So the cost of the packet with all the necessary address line was an issue. So for example, if there is more memory, so in that case, we need number of address lines is going to be more. So you all know. So if each and every address, so for example, if that memory capacity is going to be more, so in that case, automatically, indirectly, it will increase the address lines. So each and address line has been increased. So for example, if you refer to 8086 processor, how many address lines are there? There will be 16 address lines are there. So there will be something called as multiplex address as well as data. So we are going to use something called as multiplex address as well as data. Same line will be used for address, same line will be used for address. So how that multiplexer will become automatically, you have to know that the digital concept, so we are going to use multiplexer. So 0 0, it will be moved to 1. 0 1, 1 0, 1 1, some pattern, decoder is used. So in that case, we are going to use. So if you use such kind of operation, automatically the number of address lines get reduced. So that is why we are going to use such kind of multiplexer, all those things. So if it is not possible, if I want to reduce something like that, so I will use some multiplexer as well as decoder for order to get that information. So here also we are going to use that same concept, multiplexer concept. So the upper half of the address can be row access probe. We will call it as row address. Upper half means, for example, you are going to have 16 bit. Upper half means 8 to 15. Lower half means 0 to 7. So that upper half is going to be connected to lower row access probe. The lower half of address lines is going to be called access probe. So why we are going to use this kind of arrangement? We are to cutting the number of address pins to half. So we are going to reduce the number of pins. Okay, I think my point is clear. So if I'm going to use multiplexer, many to one concept. So in that case, I can easily reduce the number of lines. So with the help of decoder, I can decode which address I want to use. So this is the structure. So we have the DRAM internal structure. So we have the address register. So this is going to be it is going to be collected to the row decoder. So similarly, we are going to have data that is going to be collected to the column decoder. So we have address as well as, that is why I told you multiplex address as well as data. The same single line can be used as address as well as data. But you can ask one doubt there. How that processor know whatever the incoming signal is address or data. So for that, during the first cycle, whenever I'm going to start that operation, the first cycle. So if I'm going to use one particular operation, it will take several cycles. But during the first cycle, whatever that incoming information is going to be always call it as address. For example, it will need 5 T states required for complete that operation. In that case, the first T state will be used for address. The remaining 4 T states will be used for data. So in similar that pattern is why. That is why we are going to use the multiplexer. So the same thing will be used for address as well as data. So in that case, we are going to use the row decoder, the column decoder, and then we have some sense amplifier. So here that memory is also going to be stored as an array. So each and every, for example, we are going to have a logic 1 bit, it is going to be stored in an array. So we have some concept called memory banks. We have memory banks. So that is going to be there. So with the help of address lines as well as decoder, lower order, higher order, based on that we are going to. So if I am going to refer, so here we have that, for example, we are, you all know that DRAM is nothing but we are going to use one single transistor. So in that case, the row enable is going to be there, that is going to be used. So whenever that row enable is there, the transistor is on, the capacitor gets charged and then it will be stored in this. So if the bit line will give you that information, so bit line will give you whether I want to read a 0 or 1, according to that value it will be stored. So only one single transistor is used for in order to store the data. So bit cells are arranged in the form of memory array. So here every bit is going to be stored in an array. So multiple arrays are organized as a different banks. So if this particular arrays, so we have this group is going to be called as bank 0, bank 1, bank 2, bank 3, something like that. So that is going to be called as multiple array organized as different bank. So memory banking is one important concept in computer architecture. So we have odd bank, we have even bank, all those things. So in the computer organization, I think you might have studied that memory banks, all those things. Okay. So I don't want to give much detail about this memory banks. Okay. So typically the number of banks is going to be 4, 8 or 16 banks. So we have bank 0 to up to bank 3, or otherwise bank 0 to bank 7, or otherwise bank 0 to bank 15, something like that. So typical number of, so we have, according to that architecture, we have this many banks are available. So that is used for DRAM. So we have sense amplifier that raise the voltage level on the bit lines to read the data out. So with the help of row as well as column, we are going to have the voltage level, where either value is going to be 1 or the way 0. We have a threshold value. So within this threshold value, this is going to be either value or 0 or 1. We are going to read from the sensor. So this is the DRAM internal structure. So these are all you have to know, but you are not going to use this hardware and all, but internally how this data is going to be stored in DRAM, you have to know. That's why we are giving this detailed information. Okay, so coming to the DRAM memory technology, you all know we are going to use something called as Amdahl's law. So what happened in that processor, if the memory should grow linearly with the processor speed. So the processor, already last class we have discussed one graph where the processor speed is going to be linearly increased, as well as the memory capacity MIPS have 1000 MB of memory. So it has to be linearly, it has to increase. Okay. So the next important information is memory capacity has not kept pace with the processor speed. So for example, we should not fix that processor speed with the memory. So always that memory capacity, for example, you have 1000 MB means that much speed you are not going to get. So we have some speed, it can be achieved. Okay. The next one is DRAM. We are going to, in earlier days, it can be small boards called dual line memory module. So DIMM, we'll call it as DIMM. So such kind of arrangement will be stored. We are going to purchase SDRAM in dual memory module. Dual line module means the row as well as column. That is why the dual inline memory module. And then it will contains of 4 to 16 DRAM. So you just think about that one. So we have DIMM contains 4 to 16 DRAM. So according to that, the capacity is going to be fixed. Capacity is going to be fixed. So that is about the DRAM technology. Now we are going to compare the static RAM versus dynamic RAM. So already I told you, so we have number of transistors is going to be more. So we have a bit line. So here we have 0 as well as 1. So if you refer to that structure, we have C1, C2, that the transistor capacitor is connected to 2 transistor. So we have to C2, C1 is going to be on, C1 is going to be 1, and then C2 is going to be 0. I will read the value 1. So if C1 is low and then C2 is high, I will get the value 0. So we have back-to-back inverter that is going to be called as buffer that will store that information here. So based on the row select, we are going to get the address or something like that. So bit lines are driven by transistor. So this already I told you that SRAM is going to be much faster, but one transistor and one capacitor. So we have, for example, each and every transistor will have its it will have 6 transistor, and then it will have one capacitor that will be used. So in that case, that so that size is going to be minimum. Why? Because that size is going to be minimum means we have 6 transistor is used. So the cost is also going to be high. But comparatively to DRAM, so here the fast is going to be there. There is no additional requirement for in order to refresh that thing. There is no key point of power leakage or something like that. It is not available. Whereas in case of here, that the bit stored as charge on the capacitor. So we have a capacitance that we have a bit line, we have a row enable. So we have the row enable is going to be refreshed, connected to refresh circuit. So it will periodically refresh, and then I will get the value read 0 or 1. So there will be bit cell charge over a time. So a read operation, there will be some leakage is going to be there. So we need periodically refresh, but hence the name is going to be called as dynamic RAM. So during runtime, I will store the data. Statically, I can change that value. So if we have a dynamic RAM, so how can I improve? So how can I improve the memory performance inside the DRAM chip? So dynamic RAM we are going to have. So how we are going to improve? So we need some innovation. So we are going to use some technology, innovative technology. We are going to use. We are going to improve the design factor for order to improve the performance of the DRAM. In that case, that innovation in mainframe also need to reduce the gap in performance between the processor. So we have to reduce that gap. So memory, that speed, as well as the processor performance. So we are already told the optimization we have to done. So there should be some optimization has to be done with the access time for the memory along with the processor. So the developer has to think about the optimization methodology for in order to increase the speed of the range of using, and then bus. So we are going to have control signals, and then we are going to have wider memory. So size has to be increased, and then we have to use that bus. So multiplex address as well as data are used for order to increase. So that is that earlier case. This kind of innovative idea is used for order to increase the performance. But the one important thing is in earlier stage, so that the DRAM has an asynchronous interface. So it is asynchronous interface into memory controller. So you all know what is basically asynchronous. So randomly, so there is no, for example, there is no periodic. So randomly it is there. So you all know that if what is basically synchronous or synchronous. So there will be one clock cycle is going to be shared with the multiple registers. Whereas in case of synchronous, we have individual clock lines are going to be allowed to each and every registers or something like that. So in that case, we need some overhead. This will tends to that overhead. So whenever we are going to use asynchronous interface, so in that case, there will be speed mismatch occur. In order to avoid that, we are going to have improvements. So what is the improvement? Every transfer involved overhead to synchronize with the controller. We are going to use synchronized clock signal added to DRAM interface, reduce the overhead. In order to avoid that overhead, we are going to use this clock signal, individual clock signal. So then and there, after that, this DRAM is going to be called as synchronous RAM, synchronous DRAM. That is why that there will be S is kind of. So don't think S is nothing but static. So here it is going to be called as SDRAM. So previous slide, SDRAM, SRAM, we have used that word. S is nothing but static. But here it is not S technology. That is going to be on innovative improvements in that. So it is going to be called as SRAM. Okay, the next one is the further they are going to have innovative information. We are going to have a double rate rate SDRAM. So we are going to have DDRAM or double rate SDRAM is going to be that. That is going to be the later development of SDRAM. Once that the synchronous dynamic RAM came to existence, further some needs of improvements are required. So in that case, we are going to have later development that is going to be called as DDRAM. So it is used in the PC memory since 2000 onwards. We are using this DDRAM. What is that double data rate means? You all know there will be clock cycle. That will be, so if you refer to one cycle, there will be falling edge as well as rising edge. So each also we are going to transfer. It is called as double data rate. So previously there will be one cycle time, it will take one clock cycle. So both on period as well as off period. So, but here is that we both on period I will send the data, off period also I'm going to have. That is why it is called as rising edge as well as falling edge DDRAM clock signal. So that is why it is called as doubling the peak data rate. That is why it is called as double rate SDRAM. After that, further they are going to have some innovations that is going to be called as a graphics data RAM. So special class we have the SDRAM based on SDRAM design. That is going to be, we are going to have a graphical processing unit is going to be attached, all those things. That is that detailed study. So that GDRAM, graphical dynamic RAM is GPU require more bandwidth per DRAM chip than CPU. So it needs some additional bandwidth required for in order to have some graphical part. So it will have several important difference. So wider interface. So we need 32 buses, 4, 8 or 16 in current design. So we have the design in terms of 4, 8 or 16. Okay. So GDRAM have higher maximum clock rate on the data pins. So higher data clock, that fast. So we are going to increase the speed. So in that case, higher rate than data pins. And then allow higher data transfer rate with incurring signal. So previously we have 1 MB, 1 kbps, and then 1 Mbps, now 1 Gbps, something like that. So that is going to be called as transfer rate. Normally connect directly to the GPU and are attached by soldering them to that board. So the GDRAM is connected to that graphical processing unit GPU instead of connected to previously DRAM, SDRAM connected to your CPU, whereas in case of GDRAM, that is connected to graphical processing unit that will give the data. So DRAM normally arranged in expandable array of DIMM. So dual in memory module. Already you have studied what is basically dual in this there. So okay, so in that case, DRAM are normally arranged in expandable array. In that case, multiple banks. This and all theory. So we have multiple banks on each DRAM device. So it will use the concepts called interleaving. So one concept called interleaving, and then it will be more helpful for power management. And then, for example, it will have some blocks, 2 to 8 blocks, all those things. I just read this theory, whatever this given in the slides. So how to reduce that power consumption in SDRAM, synchronous dynamic RAM. So both dynamic power is used in read write and static or standby power. So how to reduce that power consumption? Normally we are going to use standby power mode. So we have some both depend on operating voltage. So this is the voltage range 1.35 to 1.5 voltage, all those things. So in that case, all recent SDRAM support power down mode. What is basically power down mode is nothing but if there is no process occurs, we will put it in the sleep mode. So that is no, you all know there will be a power options, power options, which will be power options, not power options. We will call it as mode of operation. What is power mode? We will put it in ideal mode, or otherwise we will put it in a power power down mode. So which means that ideal mode means the processor will be down, and then the remaining peripherals will be working. We will have power down mode means both processor as well as the peripheral is going to be down. So any event occurs, automatically it will start immediately from the current. So not just simple to that one. So you will put it, your laptop, if you are not working, that we will put it in hypernet. No. So in that case, once if you have an interrupt like switch on, immediately that processor it will resume that from that exactly where we have stopped. Such kind of things are given in this particular slide. So we have to enter telling the DRAM to ignore the clock. So this and all theory, we have some automatic refresh, all those things. One important thing is flash memory. So previously we have discussed this main memory now, that server is used with that main memory with that this kind of SDRAM or DDRAM or something like that. But if I'm going to use personal mobile devices, we are going to use the concept called flash memory. This is one type of EEPROM, electronically erasable programmable read-only memory. So if, for example, it is read-only, it can be erased. So with the help of electrical, we are going to erase it, and then it used as a back storage in personal mobile devices. Already I told you. So flash uses different architecture and has a different property than standard DRAM. So we have a separate different architecture. It is not same as DRAM. The most important difference are it can be erased before it is overwritten. So for example, I can erase and then it is overwritten. So whenever I want to, for example, if I want to write in my things, I will overwrite. I will not erase. Simply, I will overwrite must be erased before it is erased, or otherwise you can erase something like that. So nowadays, for example, if I am going to have 5, so in that case I want to write into the same memory location that 5 is replaced with 6, which means that I am not going to spend much time for erasing that content. I will overwrite that with the content, something like that. So that is the latest technology. Flash memory is static. It gets content even when the power is not applied. So it is static. So in that case, whenever we are going to use DRAM, so the charge get reduced, automatically the content will be erased. Whereas in case of static RAM, until even the power is lost, it will maintain. So that is one important. So here we are using static. So draw significant less power when not reading or writing. So that is obvious. So because you all know, so there is no leakage. So in that case, there will be power consumption will be very minimum. So this is all theory. I think you might have read all those things. What will be the size? Then how many blocks are available? All those things. Okay. So finally, we are going to see something called as enhancement in the dependability in memory system. So during the fabrication process, we are going to use cosmic rays striking memory cells, and then we are going to have if there is any error occurs. So in that case, we are changes to cell content, not a change in circuit called soft errors. So we are not going to, if there is any error occurs, we are not going to change the cell. So just simply overwrite. That is going to be called as soft errors. And then we are going to have a hard errors if there are permanent changes in that operation. If there is any problem occurs, we are going to replace. That is going to be called as hard errors or something like that. So that is going to be enhancement in dependency in the memory system. For example, how that error correction as well as the error correction and detection has to be done. That is very simple. So already you have studied. So we have single parity bit, odd parity as well as even parity. If I have the odd number of ones, that is going to be called as odd parity. If we are going to have even number of ones, it is going to be called as even parity. So that will detect one error. If I want to use multiple errors, that chip kill are introduced by IBM to solve this problem. So we are going to use, for example, multiple error or something like that. So we have already, I think you have studied in digital system how multiple error can be done, all those things. Okay, so that theory we are going to use for in order to detect error as well as detection of error as well as correction. So that is similar to a RAID. So I think in computer organization you have studied that about RAID. So how error detection as well as correction can be done in that if there is any error occurs in that data while you are going to read as well as write. Okay, so that is going to be the end of this particular memory technology optimization. So in order to summarize, what is the basics of main memory, and then what way that main memory is going to be used, what is going to be called as access time, what is going to be called as cycle time, and then what is the basic features of SRAM, what are the basic features of DRAM, how we can improve the enhancement in DRAM, and then what is the features of flash ROM, and then for example how the power consumption can be how our power consumption can be carried out. And the next one is how error detection as well as correction can be done. That is the end of your memory hierarchy as well as memory optimization, memory hierarchy as well as optimization. Okay, so with this I will stop here. Okay, so I will stop here. In that case, if you have any doubts, you can ask me next during refresh class. Just go through the video. Okay. Anything you want to convey?